It's now worth $2,500. We want to figure out how much he invested originally. So just see if you can plug the rest of the stuff into the equation. I'll give you a head start. 0.05 compounded quarterly. So now all you want to find out is P, so you just have to divide both sides. There's no logs that have to be done here. Type this into your calculator exactly as you see it, and you should get the right answer. We're not going to actually type it in right now, so we can keep going. If it's compounded quarterly at a rate of 3%, how long would it take $200 to go to $500? Again, I'll give you a second to write out the equation. How did you do? Now, what we wanted to solve for is time, and time is in the exponent. So now you have to use logarithms. So what are you going to do for your first step? You can divide both sides by 200. And if you do that, it'll make life a little bit easier. You do not have to do that as your first step. You could have taken the log of both sides to begin with. But the nice thing now is when you take the log of both sides, I'm going to take the natural log this time, then the 4t can come out in front. If you had taken the natural log right away, the 4t wouldn't be able to come out in front because there would have been a multiplication right here. And you would have had to do your adding rule first and then bring it down. Okay, so if you, again, always when you get your answer with your calculator, type it in afterwards into your original equation to see if it works. So that's a very important skill in this unit. And there's the answer. Again, you can type that into your calculator, and you know you've typed it into your calculator correctly if you plug it back into the original equation and it works. Again, we won't take the time to do the calculation. I'll leave that for you to practice. You only round at the end. Calculate the time it would take for an investment to triple if it is compounded monthly. It's a very typical exam question that people get stuck on because it feels like you don't have enough information. So I'm stuck. I know that the interest rate is 5%. I know that it's compounded monthly. I know that I'm solving for t. What do I put for the amount I started with? What do I put for the amount that it's going to be worth? You're going to start with $1. Then this would be 3. What happens if you start with $10 and this is 30? Would it give you a different answer? So if you started with $10 and you end up with 30, because that would triple, what's our first step that we've always been doing? Divide by 10, and then you get 3 equals. And what's really cool about this is with compound interest, what this means is it takes the same amount of time to triple $1 than it would take to triple $1 million. So if someone has $1, and we're going to find out in a second here how long it's going to take to triple, they're going to find out in that many years they have $3 and then dance around because they got $3 now. But the person who has $1 million in that same amount of time gets $3 million. So it's one of the reasons why if you have lots of money, you keep getting richer. And if you don't have a lot of money, you don't get richer. So it's one of the unfair mathematical things that keeps society somewhat unfair. And then I'll teach you the rule of 72. Do you know the rule of 72? Okay, I'll teach it to you after this one. So now if we solve this, you can take the natural log of both sides, or the log, it wouldn't matter which one you used. And now that 12t can come out in front. And then to solve for t, and I'm kind of curious what the answer is, so I'm going to type this one in. "22 years. So if you had $10 million in 22 years, you would have $30 million, which works out to about $1 million a year. Pretty good wage. So you just have to convince someone to give you $10 million first so that you have a good job. That would be a good idea. So go around. Could you give me $10 million? I'd like a really good job where I don't have to do anything and just the interest pays me. Unfortunately, it doesn't work like that. So the rule of 72, sometimes it's called the rule of 70, is an estimation technique to figure out how long it's going to take you to double your money. You just take 72 or 70 and divide by the interest rate you're getting. So for example, if you're getting an interest rate of 6%, 72 divided by 6 is 12. It'll take approximately 12 years to double. You could plug it into the formula and check it, and it'll be really close to 12. So it's a nice little estimation. The reason it's sometimes the rule of 70 is because if the number that you pick is closer, easier to divide 70 than it is 72, then people use that. So 70 divided by 7%, it'll take about 10 years to double your money if you get 7%. Okay? Right now, interest rates are less than 1%. I think you can find 1% some places. So let's just do a little mental math. Yeah, so right now it only takes 7 years to double your money. That's not very good. But it used to be that interest rates were high, sometimes as high as 10%, which would take you only 7 years to double your money. In 14 years, you will have quadrupled your money because you would have doubled it twice. So it can be very, very powerful. That's the rule of 72. Okay. Now, one thing that's interesting is, okay. Never mind. If you had an interest rate and you were compounding, the more often you compound it, the more times you can make money on money. So it's better if your interest is compounded monthly, because that means every month they're going to pay you a little bit of interest, and then you're going to make money on that interest for the next month. So if they paid you interest every day you'd get a little bit, and the next day you'd make a little bit on that. The way that it works is basically like this. Say you had, let's use some really easy numbers. Let's say you had $1,000 and 10% interest. So that means in a year, they would pay you $100. So if it was compounded annually, at the end of the year, they would pay you $100. If it was compounded semi-annually, twice a year, halfway through the year, they would give you $50. And then for the other half of the year, you would get the other $50 plus 10% of the 50, which is another $5. So that would be really good. If it was compounded monthly, at the end of the first month, you would get that $100 divided by 12. So that would be just a little bit less than $10. And then the next month, you'd get that again, plus 10% of that less than $10, so an extra $1. And it would slowly add up during the year, and it would be even more. So annually we got 100. Semi-annually we figured out we'd get like $105. And so on and so on and so on. Now they found out that if you kept doing this, instead of every day you did every hour, and then instead of every hour you did every minute, and then instead of every minute you got paid every second, and then instead of getting paid every second you got paid every millisecond. Right? So if you got paid every second, you would take your $100. How many seconds are there? 365 days times 24 hours times 60 minutes times 60 seconds. You wouldn't get very much at the end of a second, but you would get a little bit. And then you would make interest on that and interest on that. And the formula changes to this, where R is still our interest rate and the number E appears. So this is a natural occurrence of the number E. Just like pi naturally occurs in a circle, the number E naturally appears in continuous growth. So if they paid you over and over and over again, this is what the formula would become. But you notice that the more often they do that, they're just giving you tiny, tiny, tiny bits of money each time. So we're going to see how much of a difference this makes. We're going to do part B first, and then we'll do part A. We're going to do part B, figure it out. If you were paid quarterly, $2,000, we want to figure out the amount, 2,000, 1 plus 0.55, compounded quarterly over 10 years. How much is this amount? So compounded quarterly over 10 years, you're going to get $3,453. How much more do you think it's going to be if it was all the time? This was only 4 times a year. This is like an infinite amount of times a year. What is your guess? Get a number in your head, do your own guess, and now we're going to figure it out. And I think you're going to be surprised. Wow! You would have made like $13 more in 10 years. That's not very much, is it? Okay? I was kind of thinking that you would expect a much bigger number. But what happens is that they just keep giving you smaller and smaller amounts, and the number of compounding periods per year really doesn't make that big of a difference. What makes a big difference is the interest rate. So one bank could try to convince you, oh, we'll give you 5.5% and compound it continuously, so we'll always be paying you. And they'd probably get a lot of people to sign up for that. But if you change this to 6% instead of 5.5%, this is going to be higher. Interest rates are the key thing that affect how much you're going to pay or how much money you're going to get. Now, for the most part, most people don't have lots of money to put into an investment. But almost everybody at some time in their life has to go to the bank and ask for money. Because if you're going to buy a house or buy a car, you probably don't have enough money to buy it outright. Then they're going to give you a loan, or they're going to give you a mortgage. And the number one important thing that you can negotiate to save you money over time is that interest rate. Even if you can just save 0.25% or 0.5% over the course of a mortgage, that might become $50,000 just because you negotiated 0.5%. Here, I'll show you. I'll show you something cool on your calculator. All right. So on your calculator, let's buy some houses. So what I'd like you to do is on your calculator, go to the Apps button. And the very first button is the Finance button. This is a very helpful program built into your calculator. And the very first one on Finance is Tvm Solver. That stands for Time, Value, and Money. And what we're going to do is we're going to buy a house. Okay? And we're going to just see what difference that interest rate is going to make. How much does a house cost nowadays? $300,000. We're going to buy a $300,000 house. So you go to Apps, you go to Finance, and you go to Tvm Solver. Now, the way that this program works is you've got number of payments. Most people pay monthly for their mortgage, 12 times a year, over 25 years. That's a very common mortgage. You'll make 300 payments for your mortgage. Right now, interest rates are about 3%. So we'll start with 3% and see how much it's going to cost you to buy that house. In the future, FV stands for the future value. You want to pay off the house so you don't want to owe any more money. Okay? You're going to make 12 payments in a year, and mortgages in Canada are compounded twice a year. What we want to find out is how much we have to pay per month. That's what the PMT payments, monthly payments are. So what we go is above your enter, you've got the green word solve there. I go alpha, enter, and it solves. So to buy a $300,000 house at 3% interest, you would have to pay $1,400 a month for 25 years. Okay? That means when you finally finish paying this off, if we go 74 times 300, this $300,000 house is going to cost you $425,922. You're going to pay an extra $125,000 for your house. This is normal. This is what almost everybody does when they buy their house. They buy it for a certain amount, and because of interest rates, and 3% is a very low interest rate. Okay? But you're still paying an additional $125,000 for your house. So you say to yourself, well, what would happen if I negotiated and got 2.5% instead of 3%? How much of a difference would that make? So I'm going to solve. My payments now are $1,343. How much of a difference will that make over 300 payments? I'm going to save $20,000 just by saving 0.5%. Okay? Interest rates in the 1980s. You can ask your grandparents, ask your parents if any of them remember interest rates in the 1980s. They skyrocketed. A lot of people had to lose their houses because they couldn't afford, because interest rates went up to as high as 18%. So now, if that was the current state, and interest rates were 18%, how much does a $300,000 house cost you? Well, instead of paying $1,400 a month, you'd have to pay $4,400 a month for that same house. And that same house over, if we figure out how much in total that would be if we times this by 300, you would pay just over $1.3 million for that $300,000 house. So many people in the 1980s, when interest rates went that high, they said, no, we have to sell our house. We can't afford to buy our house. It's better for us to rent. That's crazy. Then the housing market crashes, then all the values go down, and only those people that can afford to buy them outright. Okay? But at that same time that they were charging that high percentage for borrowing money, If you had a bank account, they were paying people 10% interest on their bank accounts. Okay, that's how banks work. They're willing to give you money and charge you 4% right now, but if you keep money in their bank, they only give you 1%. So they make the difference, right? And people need to borrow money because you don't have enough money to buy your own house, so it does make a difference. Now, as far as saving you money over the course of your life, so if you can negotiate this interest rate to be as small as possible, that's going to save you money. So if you negotiate it all the way down to 2%, wow, that's really low. Whoops. Then you'd only pay $12.70 a month. And now it's under that. You still have to pay $80,000 of payments. The other big thing that's going to save you money over time when you buy your house is when you first buy your house, you're going to be younger than when you pay it off. You're going to be pretty young. You'll probably just be starting your job. And because you're just starting your job, you're making the lowest amount of money in your job. And as time goes on, most jobs you move up in the company or their pay scale goes up with more experience that you have. So after 5 years, you'll be making more money than you did when you started your job. But your payments, so here when I go, your payments, you could only afford $1,300 when you started, but it might be that after 5 years, you can afford more because you're making more money. So two ways of thinking about it. You can make these decisions. Sometimes when people make more money, they just are like, woohoo, I can spend more money. And that's great. If you want to live more expensive stuff and go to more concerts and that's what you want to do, great. But if you want to save yourself money, because right now we paid $80,000 for this, but maybe you could afford, instead of $1,300 a month, maybe you could afford $1,500 a month. So you up your payments to $1,500. Because you do that, it now takes you, well, that's 60 less, about 5 years less to buy your house. And so now, if I up my payments to that, it was at $380, but now if I times this by 243.2, whoa, 0.2, I saved $20,000 by putting an extra $300 a month towards my house. That's a lot of money. Okay? So instead of going to a couple extra concerts a month, you save yourself $20,000, but you're miserable. So maybe you have to take an in-between, right? Only one concert a month and $10,000 and you're happier. Okay? But those are the kind of mathematical decisions based on interest rates, based on exponents that you can do if you understand how this works. So I kept this video on there, so if you wanted to play around with the program but you forgot what we did. Yes? No, this you would do in applied mathematics. Okay? I'm not sure if they might use this program in Essentials. They do look at some mortgages in grade 12 Essentials, but I'm not sure if they use this program. Okay? But it's all based on the ideas of interest rates. So here, filling things in, it's worth $235. You started with $200. E, the interest rate you don't know. The time was 3 years. How do we solve for r in the exponent? Again, I would probably divide both sides first. And because the base is e, it really makes sense to use the natural log. Because when I take the natural log of this side, the 5r is going to come out in front, and I'm going to be left with natural log of e. That is mental math. What is the natural log of e? e to what power is e? Right? That's what a logarithm is. The base is e. E to what power is e? It's 1. So then this just becomes yes. Oh, I changed the I started with 3 and then I changed to 5. You ever do that in math? Just your numbers magically change to a new number? Thank you. There we go. And then when you would have gone back to check, your answer would have been incorrect. So then you have to go through it again and see where you made that mistake. Okay, again, you can type that into your calculator on your own. And I want you to try this one all the way on your own. Another place that continuous formula comes in place is represented in populations. In fact, often once populations get large, they're modeled by continuous growth. There's always people being born or dying and so on, and it's just modeled continuously. So one of the things you're going to look for is this idea of something growing continuously. Also, because they've taken this formula off your formula sheet, they will put the formula, the PERT formula, in some form into the equation. So if the population in Vancouver in 1981 was 1.38 million, it's been growing at an average rate of 1.7% per year. Find the projected population in 2011. So we want to find the amount, the initial. I'm going to put it in millions, so I just write 1.38. You could write all the zeros if you wanted to. And then E, 0.017. How many years is it from 1981 to 2011? 30 years. And it would just be a matter of typing that in. And you get an answer that would be like, well, I'll find out. 1.38. 2.298 million. To the nearest tenth of a million would be 2.3 million. This is where logarithms come in. When will the population reach 6 million? So we know that the amount is 6 million. And for our initial amount, we had 1.38. And we're wanting to solve for t. Again, since we're using e, it's going to make sense to use natural log. I would take the time to divide both sides by 1.38 first. You don't have to, but it just means you have less log laws to use. And so 0.017t will come out in front. The natural log of e is 1. And we get 86.5. What does that mean? Is that what the question asked for? In how many years? Or did it say in what year? It asked for when. So you would have to go 1981, because that's your initial amount that you started with, plus the 86.5 years. So in approximately the year 2067, 2067.5, right, is when the population of Vancouver, if it continued to grow at this rate, would reach 6 million. Yes?
Do you ever think that, I don't know, this is stupid, but do you ever think like the government's going to put in like a population cap, like,
Can't have more kids? So, well, there's always these population growths, and then at a certain point, your system can't maintain that. So you see that with certain kind of animal populations. All of a sudden, there's a lot of rabbits. They run out of food. A bunch of them die, and then it enters into a sort of a stage of chaos. And then it stabilizes again, and then it starts the same kind of pattern.
At what point will Earth reach that point of chaos?
That's what is always a question, right? Are there certain things built into, like, do we get plagues and things like this when, are those natural occurring things to create chaos? Who knows? All right. When the population of a herd of gophers was first studied, it was 15,000. 6 years later, these are the hardest population questions. 6 years later, the population is 18,000. If the population grows continuously, how long would it take to triple? So it's growing continuously. So once again, they would give you this formula if you were solving a question like this. The question is asking for how long, okay? So normally as a student, when you're asking for how long it takes to triple, you would try to fill things in. You would probably start with, well, let's say I started with 15,000, tripled would be 45,000. First question, did I have to use 15,000 or could I have used 18,000? Could have used 18. Remember when we talked about it didn't matter how long it took something to triple with your money? Whether it was $10 million or $1? Same thing here. Because once you divide both sides of your equation, it's going to equal 3. What's the rate? Because we want to find t, so for sure we want to find t. What's the rate? Okay, good. You notice that we don't have the rate. So there's two things we don't know. We want to find the time, but we also don't have the rate. So if you tried to solve it directly, which is what most people would, they see how long, they try to make an equation to solve for t, they find out there's something they don't know. So then you have to back up a little bit, and we're going to have to find r first, because it wasn't given to us in the question. It's exactly what Dawson said. We can use the 6 years. We know that in 6 years it went from 15,000 to 18,000. And now the only thing we don't know is the r. Just to do something different, every single time so far, I have solved this by dividing both sides by 15,000 or whatever number that was first, right? I'm going to, because something that's going to happen to you in a test sometime is you're going to look at this question and you're going to say, I need to solve for something in the exponent. I solve for exponents by either getting my bases the same, well, I'm not going to get a base the same with e, or by taking the log of both sides. And sometimes you're going to start by taking the log of both sides. So I'm going to show you that that's not wrong. I'm just going to show you the work that you would need to do if you did that. Now I want you to write down the next step. Because if you're going to make the mistake that most people make, I want you to make it now so you can learn from it. What is our next step? Okay, so the first most common mistake is you put that 6r in front because you look at your log laws over here and you see, oh, if I have an exponent, it comes out in front. That's true if that exponent is to the entire thing. Look at that 6r. Can you see that that's an exponent to the e? But it's not an exponent to the 15,000. That 15,000 is in front there, and there's a multiplication right there. So before you can bring that 6r out in front, okay, before you can bring that 6r out in front, you have to deal with that multiplication. Other mistakes that I saw is that people divided by the natural log of 15,000 here. Okay? We have to be careful because right now all of this is inside that natural log. Because you took the natural log of the whole side. You can't just divide by part of it because a logarithm is a function. So you have to deal with your function first. So the first step here when you're multiplying two things, you can add. And now that 6r could come out in front. These are both numbers. And you could bring out that 6r. You notice there's a log law when you subtract two logs? What is it? Divide, right? And if we had divided right at the beginning, it would end up with the same answer at that point. So it's important to notice that. Now if I want to find out what r is, I just have to divide by 6. And we get r. Now, we're going to need this r because we had to solve for r first. We're going to need this r later on. So I'm going to type this in. Natural log of 18,000 minus natural log of 15,000 divided by 6. And we get 0.03, but we're going to need all of those decimal places later on. So I'm going to store this, because it's r, I'm going to store it as r to remember it later. As far as showing my work, to show that I didn't round it in my notes, I could write it down and just do the dots to show that I continued it, or you could write a whole bunch of decimals if you'd like. But if we go back, what did we initially want to do? We wanted to find out when it tripled. But the problem was that we didn't have r. Now that we've found r, we can go back to this and solve our question like we wanted to originally. So again, I'll show that I'm keeping all of my decimal places there. This time, instead of doing that, take the log right away, I am going to divide both sides by 15,000 because it really shows us what happens when something triples. And now we're still solving for something in an exponent. Take the log of both sides. Again, natural log of e is equal to 1. So we just have to divide by 0.03. So when I go to my calculator, I'm going to have the natural log of 3 divided by, and since I've saved it as r, I can just type in r, and all those decimal places get remembered. And so t is 36.1 years. So it'll take 36.1 years for this to triple. This last question I would like you to do on your own right now. Population of a crash of rhinos. That is actually what a group of rhinos is called. The last question, that is not what gophers are called, but I use it as an experiment to see which of my classes question that and which ones are silent. You guys fall into the silent group. Some classes right away go, heard of gophers? That's not right. Does anyone know what a bunch of gophers are called? It's not a litter. Clan is close. It has 3 letters that are right. Colony of gophers. Every group of animals in the English language has a different name for when you have that group together. Murder of crows, school of fish, gaggle of geese. Yeah, you can look them all up. Right? Yes, this is in the video. So, you get a bunch of rhinos together, you have a crash of rhinos. I don't think it's true in Spanish. Do you have different names for each group of animals? No.